So we start with the control phase now. Till now, what we have seen is DMA-IC and DMA and I. In define phase, we freeze our charter. Not freeze, but not we reached the stage where we could have a solid charter. In analyze phase, we discussed about measurement system analysis, process capability analysis. After that, in analyze phase, we talked about different types of hypothesis testing techniques where we establish the facts, we quantify the facts. After that, we did failure mode effect analysis and improve phase. Now we are in the control phase where whatever improvements we have done earlier needs to be consolidated upon. You have to keep on doing that and do a continuous improvement. The improvements which you have done should not fade away with the time. They should be sustained. So in order to do that, you need to control. Now, what is the meaning of control? It's not like we are practicing a control, like we have some indicators and then if certain value goes down below that, we are going to control it. No, it's statistical control, what we are talking about. That means predictability of the process. We want to keep the process predictable up to certain probability, or you can say certain level of predictability has to be ensured in the output of the process. So that's why we make control charts. So control over here basically means statistical control, where you want to predict the output of the process with certain confidence. Now, control chart for variables. There are two types of control charts we are basically going to do in this. That is control chart for the variables and control chart for the attributes. In control chart for variables, we are focusing on those quality attributes which are quantifiable, with which you can associate a number with. So that's why we have control charts for variables. They are measurable on a numerical scale, and when there's a variability, we need to ascertain that the variability in the process is under control or not. Variability is predictable or not. That is the whole objective of making control charts. For example, dimensions given over here 40.5 or 39.5. This is the range in which certain dimensions should vary. Now, that variation is under control. Now, the kind of what kind of variation are we talking about? We have talked about this thing in earlier lectures, that two types of variation are there. There's a common causes of variation and special causes of variation. Common causes of variation are difficult to remove, but this variation is predictable. You can understand this variation. Okay, that's why you name it as a common cause of variation, which definitely is going to be there in all the output. The another cause of variation is a special cause of variation, which does not have, where this variation is not present in every unit of the output, but it may be present in some unit and maybe not later on. So with control charts, we want to remove special causes of variation. If you remove the special causes of variation, only thing that will be left with is the common causes of variation, and hence predictable. So why do we go for control charts, variable control charts? Variable control charts, the cost is generally high. This kind of comparison I'm going to do later when we talk about the control chart for variables. So I'm not going to follow these slides right now. So how do I select that which characteristic I should consider for making control charts? So a process may be having 10 different characteristics, quality characteristics, which are quantifiable. So should I be making control chart for all the characteristics? But that becomes a cumbersome process and at the same time very costly also, because taking data for 10 different quality attributes, which are variables, can be costly because I might need sophisticated equipment for that. So that's why it's not advised to do quality control charts for all the variables, but you should do it for critical ones. How do I find out the critical ones? There we've already seen some techniques earlier in Six Sigma that how do I find out critical ones. So I'm not going to focus on that. That I'll leave it to you. Like you can use SIPOC, you can use Pareto analysis, you can use CTQ, different techniques are there to find out critical, like fishbone diagram followed by cause and effect matrix. So this is one of the examples where they did a Pareto analysis and found out that uh, percentage wise, which is most critical, say inside diameter of a hub, some assembly is there, tire assembly is most critical. So you can pick up that one and make control charts, or you can have like vital few trivial many, like what the ones which are covering 70 percentage of the total defects. You can take those quality attributes. So some preliminary decisions need to be made while before I go for making control charts. First is selection of a rational sample size. So we have discussed about selection of sample size earlier in the analyze phase. I'm not going to focus on it again. So frequency of how often are you going to collect the samples, choice of measuring instruments, and the form for the collection of the data. Now, the important thing is when I'm developing a control chart, it is for the means. Let me explain you the meaning of means. So this X double bar over here, it indicates grand mean, that is mean of the means, and sigma X bar is the standard error, or you can say sample standard deviation. So this formula over here, it indicates upper and the lower control limit. So let's have a look at it. Estimate of process standard deviation is given by sigma hat given by R bar by D2. Now this D2 value we get it from some tables, standard tables are there. I'm going to talk about that subsequently. Then we have upper control limit. So we can substitute sigma as R bar by D2, and that's what we get. Further, this term R bar divided by root N and D2, it can be represented as 3 D2 by root N can be represented as A2. This is also directly available in a certain table which we'll talk about later. So a more simplified formula, upper control limit for lower control limit is X double bar plus minus A2 R bar. Similarly, this is control chart for, you can say X bar chart. These are the control limits for the X bar chart. Then you have control limits for R chart. So remember, it is not R bar chart, it is R chart, where R bar represents average range and sigma R is given by this formula, R bar by D2. Or further, it can be simplified as D4 and D3 R bar. So these two values are also available in the standard table. Now the sample size for sample size up to 8. A2 values and D3 and D4 values are given over here. So we can use this table subsequently. So what do we do after this? So we plot for X bar chart, we plot X bar values between the upper and the lower control limits and find out if there is any special cause of variation which is indicated by a point falling outside the control limits. While for an R chart, we again do the same thing. So let's take a problem. Now you can see over here there are 10 samples and the sample size is 5. So I would like to make you aware about a common pitfall, which is in this particular formula, this n which is given over here is the sample size and not the number of samples. Always remember that. We consider sample size. So for 10 samples, we have 5 sample size. Now what do we do next is we find out the mean of each sample and then we find out the grand mean, which is given by x double bar. So it indicates that. So x bar value comes out as 5.009 and r value, which is range. You can see how do we find out the range is the minimum value in a sample and the maximum value, the difference of that irrespective of the sign. We only write the positive value of that. So 0.115 is the range. So yeah, further I can get the value of upper control limit and lower control limit, 5.075 and 4.943. So these two values, now I'm going to check whether any value of x bar of each sample is falling outside these control limits or not. So 5.075 and 4.943. 5.075, so there is one value which is falling outside the upper control limit in x bar, 5.08. And 4.943, anything lower than that? Yeah, we don't have anything lower. So there is one sample which is indicating a process is not in control and there is some special cause of variation associated. Similarly, we do it for our chart and we find out these are the control limits and you can get the D3 and D4 and A2 values from the table which we have seen earlier. You can see here for 5 sample size, A2 value is 0.58, which we have substituted over here. 5.5 has been rounded off to 1 decimal place, 2 decimal places, yeah. So this is your X bar chart. You should know how to make it. On X axis, on Y axis, you have X bar values, and on X axis, you have the subgroups or the sample number. We can see this point over here is indicating that the process is out of control. Further, our chart indicates the process variability is under control. So X bar indicates the process centering, regarding process centering, or and our chart indicates process dispersion is under control or not. So what do we do next with this X bar chart? We delete this point and we again replot it with the revised mean. Of course, the mean will be revised because one may get revised because one value is being deleted over here. So this revised value of mean, you're going to get a new set of control limits and you again check whether everything is under control or not now again. The meaning of deletion of the point is that I can just go on randomly delete a point. It means that I can delete the point only when I have taken sufficient measures to identify and remove the special cause of variation. Getting it? So how do I do that? I need to backtrack. So I should know where this point is coming from. What is the history of this point? And then so that I can go and backtrack and figure out what might have caused this point to go out of control. This you can consider to be another example where you have 25 samples and the sample size is 4 over here. So I leave this exercise for you to do. There are 2 points are falling outside. So these 2 points are removed as well as 1 point from our chart has been removed. So we do this and go ahead. and getting the revised control limits. So first time when we find out the control limits, these are called trial control limits. And if everything is in control, we do not revise these control limits. In case any point falls outside, we need to find out the cause of variation. Then we need to remove that point and then replot them on new set of control limits and check again. Now here you can see one thing. If any point falls below our chart, below lower control limit of our chart, is it good or bad? Now because it's indicating range is indicating dispersion or variation. So any point falling below lower control limit would obviously indicate that the variation is low. So should I delete the point? Yes, you should delete the point, but should try to learn from the point that what is the good thing that I've done over here because of which I'm getting such a low dispersion. Okay, so this is one important thing. Another is at times your lower control limit may come out to be negative for an R chart. So in that case, you take it as 0. Now this is another example which is given over here. For example, now in this, the control chart was made and it has been found out that sample number 22 and sample number 3 are plotting outside the control limits. So yeah, so because of that, you do some investigation. They found out the high temperature was there and the wrong dye was used, because of which the special cause of variation, and the certain supplier was new. Because of that, there is a problem. So these are the control limits. So 1 point was falling below over here in X bar and 1 point over here above. Yeah. So and at times a point may fall outside the control limits and it might be just a random cause also. It may not be a solid reason for a special cause of variation. So in that case, you may have to just let it go. So a lot of background knowledge is required before you can conclude that a certain point which is falling outside is a special cause of variation. At times it may just end, you may just end up in doing wild goose chase. So that's what X bar and R charts are there. Now there are certain patterns you might observe in the control charts, and then I'll discuss one or two of them and rest I'll skip. So Western Electric Company has identified 15 typical patterns. These are some standards. You can see this is a natural pattern. You see general randomness is over here. You don't see, even if you look at it carefully, you wouldn't find any specific pattern in the variation. While here you can see there are sudden shifts, like there are levels being, you got 1, 2, 3, 4, 5, 6 points over here, then suddenly another set of points are just shifted towards the upper control limit, which might indicate that underlying deterioration in a process or certain change in the setting has happened, and it might again go one step ahead and move to the upper control limit. So these are sudden shifts. Then you have gradual shifts, like it's going down towards the lower control limits in a continuous manner. While there could be a trend. So I'll just not go through all of them, just three. You can further read it. So we finish the control charts for variables, and you can obviously post your queries to me. So next is we are going to do control chart for variables.